This meeting is being recorded.
Okay, cutting. This is the first week we actually get in the labs and make stuff. The meme channel. So this week is on the vinyl cutter and laser cutter. Easy to use tools, probably familiar, but there's much more advanced things you can do. So each week there's going to be an individual assignment. There'll be a group assignment. The group assignment is something each lab needs to do, but it doesn't need to be done separately. So you'll do it as a group, document it as a group, and then on your individual pages, you just need to point to it to show that you understand what was done in the group assignment. So you're going to vinyl cut something, you're going to laser cut something, but you need to design a kit. It needs to be parametric. It needs to account for kerf. And I'll explain all of that as parts of more advanced laser cutting. And then I talk about extra credit. Extra credit is in quotes. You don't really need extra credit, but it's just the notion that you can stretch. And here for this week, you can laser cut things that aren't just flat sheets. So we'll start by talking about tools. For low-cost cutting, Cricut is nice because they have a great collection of, well, actually, this shows the problem with them. They have a great collection of tools for their machines. So they have all sorts of embossing, rolling. You'll see these teeth. It cuts with a knife, but it's driven. It can control the angle. So very flexible tools, low-cost machine, but the software is proprietary and keeps trying to sell things. Cameo is low-cost vinyl cutters that have open interfaces that are more convenient to talk to the Cameos. We've used roll-ins for many years in Fab Labs. So these all drag a knife. And these are a few $100s. Those go to $1,000. And then Zun makes a cutter that costs $100,000 or more. These giant cutters, but they have driven tools where it vibrates, it can control the angle, it can tilt. And so these are used to make parts of Formula One race car composites and luxury leather goods and all sorts of uses for this giant $100,000 one. Other cutter, this was a project done by former students. Let's go through the ad. So the other cutter is a knife that's both vibrating and controlling the angle, and that makes it almost like a laser cutter without the laser. And the last note on cutting with a knife is ultrasonic knives are amazing products. It's a knife that vibrates at ultrasonic energy. And so when you use it, it looks just like you're holding a knife. But if you put it in plastic, it smokes and melts and you slice right through it. So those are cutting with knives. Higher end machines can simultaneously print and cut. Then we'll use lasers. So Epilogue, Universal, Trotec, GCC, they make substantial laser cutters that are workhorses in labs. These cost on the order of $10,000. Then this is a group of lower cost, more recent laser cutters, in part thanks to our friends in Shenzhen. And these have reduced the cost down to a few $1,000s. And I'll talk about later the difference between diode and CO2 lasers, but the diode lasers in particular are making laser cutting more accessible. And then at the other end, this is a company started by former students. This is about a $60,000 laser cutter. It has a fiber laser, and it's the other lasers I showed you range from like 10 to 100 watts. This is a few thousand watts, much higher power. And what that lets you do is cut metal parts, thick metal parts at high resolution. This is a laser in my lab that we used, for example, for we use this laser to micro machine single crystals of diamond to make rotors we spin at 10 million revolutions per second to study molecular structure. So it's a micro machining laser. This is another kind of laser in my lab that makes pulses of light that are, oh, I'll have to fix that link. The light pulse is a femtosecond. So milli, micro, nano, pico, femto. And a femtosecond, let's see, a femtosecond is just the light pulse is a cycle of light and ultra short pulse. And Danielle reminds me that I need to link here, and I missed the link. Fabu Laser is an open laser design created by a Fab Academy instructor that's like the industrial strength lasers I showed you, but now with an open design that you can make from Danielle and Gracia. That's an important link I'm missing here. This is the range of lasers, and in your lab, you'll have something in that family. For cutting, plasma cutters create a plasma that can melt through metal. Those used to be very messy. They've gotten better, but it's similar to welding. You have a jet of molten metal coming out, so you need to do it in a workspace where you would do welding with no fire hazard, with a concrete floor. Water jet cutters are incredibly useful. So an Omex cutter like this costs between $100,000 and $200,000. It has a supersonic jet of water that entrains a garnet abrasive, and it lets you cut through glass, stone, 6-inch steel, anything. There are these desktop water jet cutters. They cut all of the materials a water jet, the bigger ones do. You can't do it quite as thick, and the pressure isn't as strong. And so as a result, they use much more of the garnet. But these are roughly 10,000 rather than $100,000 scale. So these are incredibly useful. Hot wire cutters melt, and a classic use of them is making architectural trim, where you take foam and the wire cuts through it to cut out the foam. And then EDMs are incredibly useful tools. This has a wire. You make a plasma around it with a surprisingly low voltage, and that removes metal. And those let you make very high resolution, high aspect ratio metal parts. So we use that to make all sorts of parts for machine building. And so out of that, these are cutting tools. You'll be using one of these vinyl cutter tools and one of the laser tools. For this week, you've seen all of the CAD tools. A number of them have extensions. So Inkscape has, this is Inkscape extensions for laser cutting. Remember for this week's assignment, the parametric part. So if you're using Ryan, you can use Grasshopper. In Blender, you can use geometry nodes. I covered sketching in Blender. This is a Blender extension to make finger joints, which I'll talk about. Oops, wrong tab. Back to here. Fusion had a slicer written by former students. They've obsoleted that. Onshape Kirimoto is a nice extension for cutting if you're using Onshape. And then all of these are dedicated tools just for cutting. So Cuddle is one, Cube, Pepakura. These are all tools specifically designed to make cut patterns, versions of cutting and folding. Then once you have the design, you need to get it to the machine. So just trivially, here's a little shape cut out on the vinyl cutter. Here's the same shape cut out on the laser cutter. Each of these machines typically has a printer driver. And so the standard way you use it is just with the printer driver. There are some tools that know how to talk to them directly. So Ink Cut is Inkscape extensions for cutting. Deep Nest is a tool for nesting, which is how you fit the parts together in your sheet. And then Mods is something I wrote that's turned into a community project. And for many of these machines, this is the project behind it. Mods lets you talk directly to the tool. So I'll pick, in this case, a roll-in cutting tool. I can bring in an image, which could be a raster or a vector, and then it's going to calculate the tool path, doing the offsetting that I'm going to talk about, and then it can, from there, it can send it directly to the device. And we like to use tools that with open interfaces, so we can build interfaces directly to them. Rather, each of the printer drivers, I don't like them because everyone has a different view of how you use it, has different assumptions. We like to have a common interface across them. Ricardo's asking about cam tools for tangential knives. So more advanced cutters first control the angle and then they can tilt it. I don't know of cam tools for that. For those more advanced things, we end up writing tool paths from scratch. Question here is aiming to use the same design on all of them. No, so in the assignment, all I want you to do is cut something on the vinyl cutter. So let me talk about that, and that'll be different than the laser cutter. I've linked here to Victoria. She fell in love with the vinyl cutter. She ended up doing all of her electronics assignments by vinyl cutting. So we're going to cover multiple ways to make circuit boards, but she used the vinyl cutter to cut out the traces and talked a lot about how she did that. And I'll talk about that electronics week. She also did, let's see, let me remember which week. Was it back earlier still? Yeah. So these are just stickers she made, and I forget which week she did. Yeah, she did amazing things with the vinyl cutter. So here's another nice example of the vinyl cutter. This is a self-flapping crane. So it's an origami folded crane that can flap its own wings. And so that's all done on the vinyl cutter. So the vinyl cutter cut out the origami pattern. It made the scores for the folds. Then it cut out the circuit to drive the actuator, which we'll talk about in output devices. So with the vinyl cutter, you can make cutout letters for signs. You can do thermal transfer. So this is, you cut out in vinyl, you heat it and melt it in, and you can do thermal transfer with it. You can make pop-up cards. You can do origami and kirigami. So this is a simulator written by a former student, Amanda, where, like, if we just take that simple flapping bird, this lets you model how to fold it, and you can actually see the forces in it as part of the simulator. So you can make origami structures. A question in the chat about electronics. Let's see, let's come back here. In the electronics design week, sorry, electronics production, which is next week, I'm going to talk more about it. It's Victoria. Vinyl Cutter here is linked to her page. And then it was this, oh yeah, actually, I was looking for this. This was an incredible vinyl cutting project she did. I'll talk a little bit about why that one was so difficult. You can make screen printing. So you, on a screen, use the vinyl cutter to make a mask to spread ink. You can make masks for sandblasting in glass. You can make flexible circuits. One of the nicest things you can do is, when you have multiple electronics modules, you need wiring between them. And instead of using cables, you can actually cut out wiring harnesses on the vinyl cutter. You can make antennas with it. So for the vinyl cutter, we use some special material. So in the inventory, vinyl is just decorative for color. This looks like vinyl, but it's a epoxy film that's stronger and goes to higher temperature. And we use that, for example, if you want to solder. This is a copper tape, and the copper tape is electrically conducting for circuits. We get rolls of a masking tape, and the masking tape we use to lift up the traces and transfer them. And then this is a easily misunderstood material. This is called a transfer adhesive. And it's a roll that looks like tape, but the glue doesn't want to stick. And so you can take a material that doesn't have a backing, put it on this, and then when you remove it, the adhesive leaves with whatever you had. So it lets you put an adhesive backing on something for vinyl cutting. So those are standard materials. There are a number of different knives we use it, and you vary the angle based on the size of the feature and how thick you're cutting. Now, the issue with the vinyl cutter is you have to set the force, you have to set how fast you cut, how deep you cut. And the issue with the vinyl cutter is all of those depend on temperature, on humidity. They depend on what you had for lunch almost. So the vinyl cutter settings change. And so each time you use it, you have to make a test and figure out the right settings for it. And then we get to weeding. So Hong Hao is another student who bonded with the vinyl cutter, and he has some good videos showing the workflow. So he's going to make circuits, and we're going to look at this again in electronics production week. So the first thing he's doing is the materials you cut come on the backing that they don't adhere very well. That's their job. So he's going to use a cutting sheet. So he has a plastic sheet, then he has the epoxy, then the copper, and that helps hold the copper down so it doesn't move. He's going to do the cutting, and the cutting is fast. It takes just a minute or two to cut. But then comes weeding. So weeding is what you call removing the material you don't want. And so when you weed, there's a few tricks. Let's see, he's going to make another one. So let me go past that. Okay, so yeah, let's get up to the weeding. So when you weed, if you cut with too much force, you have a shredded mess and it doesn't stay together. If you cut with too little force, the traces don't separate and it's very frustrating. If you cut with just the right force, it works easily. And then the other thing is when you weed, you don't lift up because that's pulling the traces away. What you do is you shear. You pull in plane, not out of plane. So if you watch what he's doing now, he's just shearing it away. And typically you have tweezers to help you. And when it works right, you don't need to look carefully. You just start pulling and magically you're left with all of the traces. So he just pulls it away and beautifully you're left with the traces that you wanted, in that case, for the circuit. So the issue with the vinyl cutter is there's skill. The settings change and there's skill in weeding. Some people really like doing that. Many people find it frustrating. So it's common to say the vinyl cutter didn't work. And what that really means is just you weren't in the right parameter space for the settings. So I'd say the vinyl cutter is the most useful, least appreciated tool because you could do almost the whole class on the vinyl cutter. You could cut out a folded structure to make packaging. You could cut out your circuits. You could make labels and masks. You could almost do everything just with the vinyl cutter. It's easily missed. Rico in the chat says, weeding nightmare. It's just noting the image I showed you from Victoria was just an incredibly detailed design where if you get all the settings right, you just pull away the material you don't want. You're left with your design. But if you're either cutting with too little or too much force, you get a mess and it drives you crazy. So it can work beautifully, but there's skill for vinyl cutting. So on the vinyl cutter, all I want you to do is cut something. And the killer app for the vinyl cutter is decorating your laptop. You can make a custom logo and turn it into a laptop sticker is a classic thing to do with the vinyl cutter. So just play with it. It's underappreciated. So then we get to the laser cutter. I'd say the let's see. Leo is asking about the Roland. I don't know the Roland Truvis. So that's a large format cutter. I don't know if you can do this at high. So these are beautiful devices that let you print and cut. I don't know if it can work to this resolution. I haven't tried to do that on this. So there's sheet feeds. You can put cutting mats on it. But what I would recommend, just given the budget of your lab, if we come back to here, something like the Cameo. These are just a few $100s. Let's see, yeah. So that's $200 for the Cameo. So rather than the few $1,000 machine, I'd recommend adding one of these little high-resolution tabletop machines that have come down to a few $100s. Okay, laser cutter. So Lena did one of the best laser cutting assignments. She went way beyond the minimum needed for this week, but this was one of my favorite weekly assignments. So so she wanted to make a castle construction kit. So this is the laser cutting. And so she's got all of the settings just right. So the parts are beautifully cutting out and separating. You'll see there's no smoke. I'm going to talk a lot about that. So she's got, this is what laser cutting looks like when the settings are just right. Then, yeah, CID, are you asking a question?
Sorry, no, no, please go ahead.
Otherwise, you should mute CID. Okay. Okay, so now here's the part she made, and then she's using it to build a castle. And the castle has stairs, it has a door, more stairs. She has folded parts, and then she has a rack and pinion with gears to work the door. So all of that was just an incredible version. That's beyond the minimum that we need for this week. So for the laser cutter, they're used for marking, engraving, and you can do that with raster and vector. So at a low, in cardboard here, at a low power, you mark it, and then at a high power, you cut through it. One thing you can do with the laser cutter is, with the vinyl cutter, you cut out shapes for halftone printing. With the laser cutter, what you can do is you can make a halftone pattern. So these are dots that are cut out as little holes. And this was using an early version of mods to do that. This is a tool to do it. And when you have that, if you spread paint or ink through it, it lets you make, for example, a t-shirt that has a beautiful grayscale. When you're a slight distance away, you don't see the dots, you just see the intensity, like newsprint. So it lets you do printing with grayscale. And also when you light these, they're beautiful. If you just have uniform light, it turns it into beautiful grayscale images. So that's halftone. Let's see, the app is a 404. So I'll fix that link. So, and I'll add Danielle. But the focus for today is, so the castle laser cutter here is linked to the castle, the word laser cutter. The focus today is on Pressfit construction. So let me show you, at the bottom, I have featured assignments, and this was one of my favorite ones. This is a marble track kit. And so in this example, this is a binary counter. So he's counting in binary the number of marbles. And so in cardboard, he's cut out a kit of parts that lets you assemble marble tracks. So that's a classic example for this week. Let's see, Rico's noting Inkscape can halftone. I didn't realize that, Rico. So let's go back to the laser cutter. This is a FreeCAD file, and in it, I describe a whole series of joints. So again, here, let me go back and forth. Keep in mind this image of these parts snapping together to make a marble track. So to make the joint, the simplest joint is this first one where you just make a slot and you fit them together. That one is very frustrating compared to this one, which is the chamfer. So the issue is, if you make a chamfer that looks like that, this chamfer is doing two things. One is, if you come in misaligned, the chamfer helps rotate it and align it vertically. And then the second thing is cardboard, which I'll talk more about, has corrugations. And so when you push the cardboard in, it gets slightly compressed. And so if we go to Sean's example, if you look carefully at his images, you'll see these chamfers. If you don't have a chamfer, it's frustrating. You have to align it really carefully. If you add the chamfer, it's much easier to assemble. It looks almost the same. You can barely see it, but it's much easier to assemble. Now, that works by you compress the material when you assemble it. It's very sensitive. You have to be within a few thousandths of an inch. If you're slightly too small, you can't fit it in. And if you're slightly too large, the joint doesn't hold together. The window where you get a beautiful press fit joint is within just a few thousandths of an inch. And we'll talk more about that in the toolpath. So chamfer compresses the material. Snap fit, instead of just compressing the material, it has a bump and you slide it and the bump goes into a slot. So the bump helps hold the joint together rather than just friction. But the problem with snap fit is you're compressing the whole body of material. So the flexural joint, this one, has a beam that bends. And this is how things like a buckle on your backpack works. The flexure bends the beam and then goes into a slot. But now by adjusting the width of the beam, you can adjust the force to put the joint together. And so the flexure makes a stronger joint that you can adjust to the material. But the strength of the joint is the energy it takes to deform the flexure. So a pinned joint is where you slide the two parts together and then you add a third part that's transverse, a pin that goes in the joint. These are the strongest joints because the pinned joint, now to separate the joint, you actually have to shear the pin. So it's an extra step to pin it, but that makes a much stronger joint. So those are axial joints. Then often you need to make right angle joints. A common thing you'll see with the laser cutter is finger joints. So they're called fingers because it looks like that. You have fingers that come together. These are common, but they're not very good structurally. They don't hold very well. One step better is to make a flexure, but you can use it in a right angle joint. And then a second step better than that is a pin joint for a right angle joint. A common thing in woodworking is a wedge joint, where the press fit, you need the tolerances very close, within the few thousandths of an inch. In the wedge joint, you put the parts together, and then this part, the transverse part you're putting through, is tapered, and you just tap it in until the wedge is the right thickness. And so that's very forgiving. You don't need the dimensions exactly right. You use the taper of the wedge to just adjust to where it's the right thickness. And it's a very strong joint because you're using then the wedge as a transverse constraint. So that's the hierarchy of joint designs. The most straightforward thing for you to do this week is a press fit joint with a chamfer, but there's a range of types of joints you can use. Let's see. Adrian is sharing this. And so what he's showing here is this part of the group assignment, where what I want you to do is vary a slot size by just like thousandths of an inch in small steps, and check to see what is too large and what is too small. And they'll all look the same, but they'll range from you can't assemble it to it doesn't stay together. And in between, there's a range where it fits perfectly. So then this next example is GIC. I was showing my children when they were younger how to use a laser cutter. They thought the laser cutter was interesting, but my project was dumb. And they had the idea of making a construction kit. And it started as my daughter is Grace. It was Grace's invention kit. And then Eli joined, so it was the Great Invention Kit. But it's a construction kit you can make from cardboard. This is a really fun Fab Lab project with kids. If you make this, it's like Lego, but you can make as much of it as you want and take it away. So what I've linked here is the FreeCAD file for GIC. And then this shows you all the things I want for the design. So on the left, you'll see an assembly that shows how the parts come together. On the right, you'll see the GIC parts. And then I have it linked to a spreadsheet. So if we so here's the sketch. And the sketch is using the constraint solver to do all of the dimensions. Now I'm going to go to the spreadsheet. And in the spreadsheet, I'm setting the thickness of the stock, the depth of the joint, all of the parameters of the design. And you'll see when I change the spreadsheet, it propagates through the whole design. So the design adapts to the spreadsheet. Here I'm showing, I'm setting. So let me jump to one of the main topics for today is offsetting. So the laser beam, typically, a typical dimension is 10/1000ths of an inch. But I just said the joints need to be accurate to 1/1000th of an inch. So what that means is if this is the part you want to make, you need to offset the path by half of the tool diameter. And so beginner laser cutting is cutting on the line. More advanced laser cutting is offsetting to account for the kerf. K-E-R-F, kerf, is the material that's left behind by a tool when it passes through. So what I'm showing here in this part is most CAD tools know how to offset. So there I'm showing offsetting in the CAD tool, and you can offset in the CAM tool, which I'll talk about. But this is an example for this week's assignment of making a parametric design linked to the dimensions, and then the whole design adjusts based around the cardboard. So that's an example of designing a construction kit with a parametric design for GIC. One other note in laser cutting is if you do something like what I showed, where you make a beam for the joint like that, if you make sharp corners here, this is going to try very hard to fail because there's stress concentration. And so just a design thing to be aware of is if you fillet or chamfer, then you spread it out and the joint won't fail at the sharp corner. So you need to be aware of sharp corners concentrate stress, and that's typically where the material fails. Then beyond just cutting, there's a number of things you can do. So these are living hinges where you start with cardboard and then you cut a pattern, and that pattern lets you fold it. So you can start with a flat sheet, but then you can have curvature like you saw in Lena. Then these are flexures. I'm going to show this in the wood machining, in the large machining week, but you can do this with the laser cutter. So if this starts with a flat sheet, but by cutting a pattern of these flexures. You can have a flat sheet that bends. This is called kerfing, where you don't cut all the way through. And so on the outside, it looks like a smooth surface. And then on the inside, you have these slots that let you fold it. And then this is a MIT thesis. That's one of my favorite ones. And I'll jump ahead to, this is about using flexures to make mechanisms. So there's a figure, let's see, maybe I went too far. Let me take a minute to find the right part of this. Okay, I'm almost where I want to be. Okay, so there's a lot going on here. So this is cut out with the laser cutter or the water jet cutter or vinyl cutter. One beam bends. If you have two beams together, they do parallel transport. So if you have two beams, with one beam, the angle changes. If you have two beams, this stays horizontal. But as the beam bends, it's moving vertically. But if you have two beams going in one direction, then you have two beams in the other direction. So I don't have enough arms for that. But if you have two beams down and then two beams up, this moves purely horizontally. Then if you do it in the other direction, you have an XY motion system. And so we're going to cover all sorts of bearings and drives to move things. But this lets you make a motion system with no moving parts. So you can make a 1D version. This is a 2D version. You can spiral them to make a rotary version. And it lets you make mechanisms. And these are used in the highest resolution, highest performance tools, because unlike something with screws or bearings, there's no moving parts. You're just moving the material. Now, the downside of this is the range of travel of the flexure is about 1/3 the size of the total system. So you can't move from one end to the other. The system has to be 3 times bigger than the range of motion. But if you can afford that, it lets you make all sorts of mechanisms just by cutting them out. So yeah, the question is about gyroscopes in drones. It's not unrelated. Accelerometers are interdigitated flexures. A common gyro is you have a triangular shape and you propagate a sound down it and you look at how it moves around the shape. So by thinking about flexures for this week's assignment, you don't have to make just a static. You can have doors that open, flaps that move. You can make complex mechanisms just by cutting out flexures in it. And this was a thesis from a student, which is now actually turned into 2 different startups that spun off from it. Where actually, yeah, this is related to the question in the chat. So let me get to his images. So yeah, we're almost where I want to be. So what Prashant is making here, okay, good. So this is a micro electromechanical system. Earlier today, we talked about accelerometers to measure motion. So the motorcycle in Kerala going around the corner. In an accelerometer, the common way they work is you have fingers that are fixed, and then you have fingers on a flexure that can bend. And then you measure capacitively the motion between them. And in this thesis, Prashant describes how he's making these just with a laser cutter. Now he's doing it at micro resolution with a micro machining laser, but a fun thing you could do is you could do this at a coarser resolution with your lab laser cutter, and you could actually make micro electromechanical systems. So that's designed for laser cutting. Let's talk a bit about the lasers. So laser comes from light amplification by stimulated emission of radiation. And so in a laser, just schematically, there's a material that has a ground state. Energy comes in and it pumps it into an excited state. And then there's a lasing transition where this relaxes and emits light. And then it goes back to the ground state. But if the pumping energy drives the system up to here, light coming in can stimulate the emission of light down to there. And so there's a lot of quantum mechanics behind that. But the main thing to take away is in any laser, you're creating a population inversion. You're pumping to an excited state in a gain medium. And then you need to pump the gain medium. And now the laser puts all of this between mirrors. And these are very fancy mirrors because one photon in makes two photons out. But if the photon gets absorbed in the mirror, it won't laze. So these are very high reflecting mirrors. So each pass back and forth, it amplifies. So one becomes two, becomes four, and you get more and more light coming out. And then finally, there's an output coupler that lets a little bit of the light out of the laser. So it means the laser has a cavity with an output coupler. And then an important parameter for the laser is typically the mirrors in the laser are focusing. And then on the output side, the output optics do something that looks like this. So I'm drawing the shape of the beam coming out of the laser. This is called the waist, like your waist. So the beam waist. The beam comes down to a waist and then diverges. And that's going to be very important for focusing it. And the size of the beam waist is the resolution of the laser, the smallest feature you can make in the laser. Most of the time, when we're laser cutting, you want the beam waist to be where you're cutting, so you make the finest features. Occasionally, we intentionally defocus. If the laser beam is too fine, sometimes you need to blur it out a little bit, but typically you want it for the finest features, so you need to focus it. So in the laser, there's the gain medium. That's the thing that we're pumping. Far and away, the most common is CO2, and these have been commodified. See, Ronald, are you asking something, or do you need to mute? So these have come way down in cost, again, and typically thanks to our friends in Shenzhen. So these are CO2 laser tubes. CO2 is the most common laser. The wavelength that it lasers at is a function of the energy distance between the pumped state and the lasing state. That energy difference is the wavelength. So CO2 is far in infrared. An issue with that is you can't see it. So I'll talk about safety shortly. You can't see the beam in a CO2 laser. Typically, they have an extra beam you can use to see where it's going to be, a visible one. But you can't see the CO2 beam. That's far in the infrared. CO2 does a great job with wood, with acrylic, for example, with cardboard. Fiber lasers are an optical fiber that's doped, and the optical fiber itself is the laser medium. They're typically around 1 micron. That's a good wavelength for cutting metal. We'll see in Electronics Week, you can use it to remove copper. See, I'm going to mute all. I muted Sumit. Fiber can mark metal. So CO2 doesn't do anything to metal, and you don't put metal near a CO2 laser. A fiber laser can mark metal. With more power, you can cut metal. And the other thing the fiber laser can do is fiber lasers can selectively oxidize alloys like titanium and grow an oxide, and the color depends on the growth of the oxide, and you can actually make beautiful color on metal by engraving with a fiber laser. And again, thanks to our friends in Shenzhen, these have come way down in cost. These used to be tens of thousands of dollars. Now there are these few $1,000 fiber lasers. Leo, cutting thick metal is thousands of watts, but tens of watts are enough to remove copper for circuit board traces. So the power is a strong function of the thickness. And I'm currently testing these little engraving lasers to compete them against the more expensive ones for cutting metal. Sumit, I just muted you again, unless you intend to be talking. Yeah, nice diagram in the chat showing what I'm describing. So fiber lasers are good for metal. Then these are solid state lasers. And there's been an explosion in diode pump lasers that make less heat. They're more efficient. CO2 tubes have a lifetime. Over a few years, their power droops. The diode lasers have longer lifetimes. And so these are slowly starting to displace the CO2 lasers. And then these are shorter wavelengths we use for there are a number of applications where you need higher energy and shorter wavelength for higher resolution features. Now, what does a laser cutter do? So let's see, the thesis I was showing was about that link was here under mechanisms. So sorry, Sumit, do you mean to talk? Okay, please don't unmute. Okay, so what does a laser do? A laser doesn't make material disappear. It's actually really messy. Depending on the material, lasers can burn the material, they can melt it, they can evaporate it, and they can ablate it. You just blow it off. And typically it's not any one of those. There are a number of different mechanisms going on with the laser cutting. And so that comes to why airflow is so essential. So when the laser beam comes in and hits the material, where the laser is doing its work, it's trying to set wood or cardboard on fire. If this is a plastic, it's releasing all sorts of hazardous gases. So all kinds of stuff gets released from the process. And you don't want that in your laser cutter, and you don't want to breathe it. So a key part of laser cutting is the airflow. So there's an air assist where you push air from above, and then below you have an exhaust pulling it out. And so the air assist is trying to, from above, it's pushing the combustion products down, and then the below, it's pulling them away. When that works right, you don't see anything and you don't smell anything. When it works wrong, you can smell the laser cutter. And if you look at a laser cutter and you see smoke in the cabinet, it means the exhaust isn't working. You need to vent it. And actually, I'll talk about that in safety for venting. So the laser might be the most dangerous tool in your lab. This was my lab at MIT. There were students working late at night, laser cutting. They got bored, they went off to read their email, and then they were wondering why there were fire trucks outside the building. What happened was the belt that moves the laser head broke. It stopped moving, and the laser kept putting all the energy in one place, and it eventually ignited. So almost every fab lab at some time has had a laser cutter fire. At MIT, we make students take a laser cut training class. So there are classes of lasers. Class 1 laser is a laser you can be around without eye protection, where everything is enclosed. Beyond that, lasers are much more dangerous because the beam can come out of the cabinet. So the first thing is venting. You ideally vent your laser to the outdoors. There are filters you can have in your lab, but we don't like the filters because they don't filter everything, and you need to keep replacing the filter. Venting outside is a bad thing to do if you're doing it near, say, a sidewalk where people are working. You want to vent away from people, so up on the roof or away from the building. But laser cutters are happiest if you can vent outside. Then you need the air pulling combustion products down out to the vent. When you finish laser cutting, it outgasses for a few minutes. If it's plastic, chemical products come out. If it's wood, combustion products come out. So if you laser cut and right away open up the laser cutter, you'll be able to smell it. If you come into a lab with a laser cutter and you smell a bad smell, you should yell at whoever was laser cutting. When you're done laser cutting, you just wait. You wait just a couple of minutes, laser cut, and then finish and let the exhaust products coming out. Whatever you're laser cutting travels in the cabinet. So over time, it gets deposited on the lens. That's not a safety hazard. It's a hazard to your lab budget and the well-being of your instructor, because if you get too much deposition on the lens, eventually the lens will crack because it absorbs energy. So one of the skills you're learning is cleaning the optics. So you get the high reflection without absorbing energy. And so the most important thing to take away from that is if this is your laser cutter in the lab. And let's say it's against a wall and it has a vent. You should have drawn on the ground a boundary. And the idea is when you're laser cutting, you can't cross the boundary. The key thing is all laser cutters are always trying to catch on fire. Let's see, Adrian, I think, has an example. Yeah, that's a nice example of what I'm describing. So when you're laser cutting, if you're there, you can prevent the fire. If you turn your back on it, then it can ignite. So you're laser cutting, you're putting a lot of energy into a small space. If you're cutting cardboard, which I'll talk about in a minute, it's trying very hard to ignite. The lasers are interlocked. So if you open the lid, you turn the laser off. If it's just at the edge of trying to ignite, but just sort of burning a little bit, if you open the lid and turn off the laser, typically that's enough to stop it. But if you really started a bad fire in the laser, if you open the lid, it actually gets worse because you've got all this airflow coming in to feed the fire. So that's why you need to have next to your laser something to fight the fire. And the best way to do it, you can have a blanket, but a really good way to do it is to have a piece of stock the size of your bed, and you just smother it. So if the stock begins to ignite, you just drop this safety piece of stock on it, and it smothers it and cuts off the airflow. And as long as you're there, that's easy to do. It's safe. There's no problem with it. If you turn your back, it's a serious issue. So that's safety. Now we come to materials. So Epilogue, one of our vendors, has a nice list of all the materials for laser cutting. Far and away, my favorite material for the laser cutter is cardboard. So cardboard in the US is rated by Edge Crush Test. And this is one way we order it. These are shipping pads. And it's very easy to describe the difference. Bad cardboard, if you bend it, will kink. You get a sharp corner. Good cardboard, if you bend it, bows. The whole thing makes a smooth curve. If it's bad, you get a sharp corner. If it's smooth, it bows. And so to order cardboard for the lab, we get these shipping pads. But you should get in the habit of, whenever you get a box, just take a flap and bend it. And if it bows rather than kinking, that's good cardboard. You can cut it up and you can use boxes that come to the lab as a source of cardboard. And the one other thing to be aware of is cardboard has a corrugation. And so in designing the joint, you want to design it to compress the corrugation. And so there's a 90-degree difference. And depending on what you're designing, it can make sense to rotate the cardboard for the angle of the joint. So cardboard is a great material. It's renewable, recyclable, light, surprisingly strong. You can, again, do much of this class just with cardboard. And I'll talk more about cardboard in large machining. You can make furniture out of it. But far and away, cardboard is the best material to use for this week. You can laser cut wood. The issue with wood for laser cutting, and there's special wood that's optimized for laser cutting. The issue for laser cutting wood is the dimension can vary quite a bit. And as long as you can calibrate it, it's okay. But if it varies over the stock, then it's a problem. And so for laser cutting, you need wood with good tolerances. Acrylic laser cuts easily. You know, it's not a recyclable, renewable resource. It laser cuts nicely, with the one note that it outgasses. But some nice properties of acrylic. One is you can glue acrylic, but it's not even really quite glue. It's actually melting the acrylic to make a really good joint. Then acrylic, once you cut it, you can heat it and bend it to make curving joints. And one of the neat things you can do, this is a colleague at MIT who showed that what they're going to do is laser cut acrylic, and then they're actually going to use the laser to bend it. So they cut out of shape. Now they defocused. They move further away, so it's out of focus. And they're using it to heat it, and they're actually bending a joint. So they're laser cutting a folded structure all in one go. And so let's see. Adrian reminds me, let me copy this link, that the hero of laser cutting was Bartholomew, who made all of these giant, he made a whale creatures, all sorts of giant cardboard things. So this life-size whale, he was the master of cardboard. You can, so acrylic also cracks easily. Delrin deforms more nicely rather than cracking. It's a bit softer. It's very smoky in the laser cutter. You need to clean it. Fabric cuts easily. You can laser cut pasta. Pasta works great in the laser cutter as a renewable material. Now, PVC, polyvinyl chloride, you don't laser cut. That releases chlorine. That's bad for you and bad for the laser cutter. You can't tell what's PVC by looking at it. If you put it in a flame and you see color, that's one clue you can use to test. But the main point of this is don't cut unknown material. You should know the provenance of plastic going into your laser cutter to avoid PVC. And then you have to avoid polycarbonate. Polycarbonate is a very strong plastic, and you need a very powerful laser to cut it. With a less powerful laser, it just smokes and makes a mess. Then metal is sensitive. You can mark metal in a fiber laser, but in a CO2 laser, it doesn't do anything. And in fact, what's very bad is if you put shiny metal in a CO2 laser, it won't cut it, but it'll reflect the energy back into the tube. And it's not designed for that. You don't want to reflect energy back in the laser. So for a CO2 laser, there are materials, Ceremark is one, that you can paint on. That's not enough to cut it, but it absorbs the energy to mark it. And then again, with a fiber laser, you can mark it, and a much more powerful laser, you can cut through it. Now, the laser cutter has a bigger set of settings. So the focus is the distance. If you're out of focus, the cut isn't as clean unless you intentionally want to do it like the example I showed you. If you don't put in enough power, you don't cut through. But if you put in too much power, you melt or burn the material. So the right power depends on it. The speed is critical. If you go by too quickly, you don't go through. But again, if you go too slowly, you're putting too much energy in one place, so you burn or melt the material. Then most of these lasers are pulsed. So the pulse rate if the pulse rate is too slow, they're too spread out and you get crude features from it. But if the pulse rate is too fast, again, you can get too much energy in one location. So you need to set the rate. Then passes are, oh, in the chat is a nice BART special. Depending on how powerful your laser is and how thick your material is, you might not make it through with a single pass. You might need to go over a few times, where if you put too much energy in one place, you burn or melt it. So you put just enough energy and it goes partway in, and then you take a few passes through. You need to place your part and understand the coordinate system. And then typically vectors let you pick vector or raster. So vector is you follow a line. Raster is you just go back and forth and you vary the laser power. So raster is good for images. Vector is good for engraving and cutting out shapes, but you can halftone with vector. Raster images depends on how the material responds to varying power. Halftone images only use one power and vary the dot size. And so sometimes that can work better than halftoning the image. So as a group, you need to learn how to focus. Oh, actually, let me add a note to the group assignment, which is to do your laser safety training. Then you need to learn how to focus the laser. And it's a good exercise to see what it looks like to cut in focus versus out of focus. Then for the material you'll be using, make a test pattern where you vary the power, the speed, and the rate, and look at what it looks like for each of those settings. And for low settings, you can mark, and then for high settings, you can cut through. But on one side, it doesn't do anything, and on the other side, it makes a mess out of the material. Then, like the example Adrian showed, make a test pattern where you characterize what is the kerf of your laser, and then find the joint size. Then I want you to design a kit for the laser cutter. It's parametric, which means you have numbers you can enter for things like the slot depth and the stock thickness. As part of the group assignment, you can test different types of joints. And then I want you to account for the kerf. Again, beginner laser cutting cuts on the line, more advanced offsets for the tool. You can account for the kerf in the cam. For example, mods can do that. Or you can account for it in the CAD using offsetting. But I want you to explicitly account for if this is the size of the part you want, you need to offset the laser beam by half of the beam kerf. And I want you to do that to get good quality joints. And then as a design exercise, try to think of a kit that you can assemble in more than one way. So don't just make a box, make a set of parts for some purpose. You could make plants or marble tracks, or like the Lego example, come up with a system that you can assemble in more than one way. And then rather than just making flat things, have hinges, have kerfing, have flexures. Try to think about a way to cut flat things that become curving things that come out of plane as just a design exercise. Okay. This is a fun week. This is very expressive. Invariably, people do really interesting things. That's laser cutting. Then reminder on the global open time for any question on anything, Saturday at 10. Monday at 9, we have the very important AI recitation. And then next week, we'll start electronics production. And also remember, new eval is now open. And so each week, you and your instructors should be working through evaluating your work to keep up with that so it doesn't pile up at the end. Any final questions or comments? Leo is asking about cast versus extruded acrylics. Let's see, the difference in cast versus extruded acrylic is the tolerance on the joint. I don't have any strong notes on it because I personally avoid acrylic. I don't like using non-renewable materials. I don't like the chemicals released. I try to stick to renewable materials on the laser cutter. If you look at a vendor like MasterCard, you can see the difference in the specs for them and the difference in the cost for them. Let's see, in the chat is Bart, more Bart pictures showing his amazing cardboard production. And that ranged from the laser cutter up to using the large format tools. Okay, this should be a fun week. Remember to document as you work to keep up. And I'll see you for the AI recitation. And I look forward to seeing your vinyl and laser cutting. Bye-bye.
Fredrik Kalle.
Ciao, ciao.
Bye.
Hasta pronto.